Hello Science Alliance, hello, I am Lara. This is IGCSE for Waves Lesson 3. We are doing reflection. If you have been to my Facebook group, excuse me, you may have a worksheet for this. If you haven't, doesn't matter at all. Doesn't matter at all. You can just do some sketches or just think about it. But they are there if you need it. Also on my Facebook page is on my Facebook page, not in my Facebook group, on my page is a post saying if you want to ask any questions or comment or just say hello during this lesson, you can go over to my Facebook page and do it there, and then I'll read it out at the end. Right, just have a look around you, okay? It seems very obvious, but have a look around you. Everything that you can see, you are seeing because light is bouncing off it and into your eyes. Everything that you can see, you only see things when light waves bounce off them and go into your eyes, which is to me, when you actually think about it, quite remarkable that you can see everything. You would, your eyes are quite small, right? You'd think that something maybe at some point light wouldn't bounce off it straight into your eye and you wouldn't be able to see it. Maybe there'd be patches of black around the room, but no, if you've got typical human eyesight, that doesn't happen. The only time that happens, excuse me, is how stars twinkle. That's why stars twinkle. Stars are very far away. Light has to travel a long way to get from a star into your eye. And sometimes it just doesn't make it. Sometimes the atmosphere just bounces the light around so much that it doesn't make it into your eye. And that's when the light just kind of goes off. You don't see the star. So that's why stars go twinkly. That's why they're black, shiny, black, shiny, black, shiny. The moments where they are kind of switched off is where the light from them just happens to have not hit your eye. But apart from stars, everything you see, you can see because light is bouncing off them all the time. So let's not use the phrase bouncing, let's say reflecting. In fact, all the waves that we have looked at, if you've been to the previous lessons, microwaves, radio waves, sound waves, they can all reflect off things. But today we're going to focus on light and we're going to focus on mirrors as well. So I'm going to talk about plane mirrors. A plane mirror, it just means a flat mirror. So for you, it's just a mirror, basically. We're not going to cover curved mirrors anyway, but a plane mirror in physics means a flat mirror. There's a certain way you need to draw it. So here's a very basic way of drawing a light ray being reflected. Let's say there's a person, right, and they've got a duck on a shelf above their head. This is how you would draw the plane mirror. It's just a line with some little diagonal lines coming off it. This is how you draw the normal. This will make sense to you later, but the normal is a dashed line which goes at right angles to the plane mirror, kind of cuts it in half. And then how you draw a ray of light is just an arrow, a straight line with an arrow to show which direction the light is travelling. So if this person is seeing the reflection of the duck in the mirror, light is shining from the duck, bouncing off the mirror and then into the person's eye. All right? Simples. So light always travels in straight lines. It can be bounced around, like I say, it can be scattered, and we'll look at refraction next week, but it always travels in straight lines, which is important for later. It's also important to remember this is a very simplified diagram. This is just how you draw ray diagrams. Obviously, light is bouncing off the duck in all different directions, but we're just going to show the one line for today. All right, what I'd like you to do, please, this seems like a really obvious first task, but it catches people out all the time at GCSE. I have some fish here. The fish are looking at the reflection of their food in their tank. So this is like the wall of the tank. The fish is looking at the wall of the tank, but it can see a reflection of the food, which is behind it, I don't know. So I want you to just draw arrows to show the direction that the light is travelling in. That's it. Like I say, if you've got the sheet from my Facebook group, then you can actually do it on the sheet. If not, I've tried to make it very simple. You can just sketch it very quickly, or you could even just think about it, but think carefully. 10 seconds, not supposed to be very complicated, this. I tell you what, you've got as long as it takes me to get a glass of water. The water is in the glass. Have you done it? Which way is the light shining? Okay, so light is shining, in this case, from the food and into the fish's eye. That's how the fish sees the food. Light is shining from the food, so the light, from the food, and into the fish's eye. This seems really obvious, but this is a mistake that pretty much everyone makes at GCSE. they get a face, they get, I don't know, a cupcake, and it's like, oh, how does the person see the cupcake like this? Ooh, I am seeing the cupcake. No! Unless that person is Superman, this is not right, is it? Light does not shine out of human eyes and onto things. That is not how humans see food. How we see food is when light shines, bounces, reflects off the food and into our eyes. It looks painful, but this is the correct way of doing things, and it's so easy to forget. Okay, let's have a zoom in then at these angles. What a great sentence. Let's zoom in on some angles now, right? This bit here, what is happening when the light bounces off the mirror? We need to learn some cool names for things. I don't think I have to teach you this bit, I think you're going to know. There's a special name for the ray that shines onto the mirror. There's a special name for the ray that shines off the mirror, and this is why we had the normal, see, because we're talking about these angles. There's a special name for the angle between the normal and the ray that shines on, and there's a special name for the angle that is between the ray and the normal on the other side. And here are the names, but in no particular order. Incident ray, reflected ray, angle of incidence, and angle of reflection. I think you've probably not heard the word incidence before, but I think you might have heard the word reflection before, and I think if you know one of those, if you can work out one, you can work out them all. So again, I'm just going to give you 10 seconds. You can scribble it down if you like. It's all on BBC Bite Size, isn't it? Just think about it. Which one is which? Have you got it? 5, 4. Okay, so I was thinking you would probably be able to work out that the ray of light that is bouncing off the mirror is the reflected ray, right? It's the ray that has been reflected. And if you can work that out, you can work all the others out, yeah? Because there's only one other ray. So the light ray that shines off the object and onto the mirror, that is called the incident ray, all right? And then when it bounces off, that's the reflected ray. So the angle of incidence is the one between the incident ray and the normal, and the angle of reflection is the one between the reflected ray and the normal, okay? So, have a go at this then. Let's annotate our diagrams further. These three fish, if you've sketched them, then you can do it on the sheet or whatever, or just think about it. Label the reflected rays with an R in each diagram, please. Label the reflected rays with an R, label the incident rays with an I, and sketch the normals. The first has been done for you. Again, just 20 seconds on this. We're just rattling through this just to sort of check your understanding. And then we'll get to my quiz. My just the right level of hard quiz. Okay, here we go then. The reflected rays are the ones that are bouncing off the mirror, right? Into the fish's eye. So that's the reflected ray. That's the reflected ray bouncing off the mirror and into the eye. And that's the reflected ray. And the incident ray is the other one, the one shining onto the mirror. That's that, and that's that. And the normal always is at right angles to the mirror, okay? It doesn't have to be in the middle of the mirror. It could be up here. It's just wherever the rays are. And it's always a dotted line. Okay, you ready? Yeah? Are you sure? Oh, what's this bit? I can't remember what's this bit. Oh, yeah. Do you notice anything weird about the angle of incidence and the angle of reflection? Notice anything here? Seeing any kind of physical, maybe law that we could possibly mention here? They're always the same. The angle of incidence and the angle of reflection, they're always the same. How good is that? Nice and simple. And that is called the law of reflection. Hey, we got that. That's the law of reflection. Right. Now we can do my quiz. Here we go. So I have some ray diagrams here, and I'd just like you to say, are they right? Are they fine? Or is there a problem with them? And if so, what is the problem? So are these okay? And if they're not, what's the problem? Here we go. That's your first one. So you've got light shining off a duck, being bounced off a mirror into a person's eye, and the angle between the normal and the ray going in is called I, and the angle between the ray coming out and the normal is called R. Is that okay? 5, 4. Some of these are so subtle, even I'm going to have to think about it. 3, and I made them. 2, 1. Yes! I'm saying yes, that's fine. Incident ray, angle of incidence, angle of reflection. Yeah, that's fine. That's a good ray diagram. Next one. What about that? Is that okay? Is that all right? 8, 7, 6, 5, 4, 3, 2. It's nearly fine, isn't it? We've got the incident ray, the angle of incidence, the angle of reflection. They're both equal. Did you notice that the normal is a solid line and not a dashed line? It's not good practice. I don't know if you ever lose marks for it on an IGCSE, but you might do. It's not good practice because it could easily be confused, couldn't it? With a ray of light or a mirror. Make it a dashed line, the normal, please. Well done if you got that, not as hard. This one, is this okay? So we've got a dashed normal, the light going into the eye. We've got the angle between the mirror and the incident ray labelled with an eye. 3, 2, what? No, it's not, is it? It's easy to see now. It's when you're panicking in an exam, it's very easy to do. We've accidentally labelled the angle between the mirror and the ray. No, that is not the angle of incidence. That's the whole point of having a normal, right? So that you can measure the angle between the normal and the incident ray. So that's the angle of incidence. That is not anything. Next one. Is that all right? 8, 7, 6, 5, 4. Husband blowing his nose. 2, 1. It's fine, isn't it? That's all right. I just replaced the duck with a carrot to try and confuse you. I wasn't fooling anyone on Facebook yesterday. You IGCSEers, you're pretty sharp. Is this one okay? 8, 7, 6, 5, 4, 3, 2, 1. Is it okay? No, it's not, is it? No. The angles have been labelled incorrectly. This is the incident ray. It's the ray shining onto the mirror, so that should be an I, not an R. So the I and the R are mixed up. And finally, is this one okay? 8, 7, 6, 5, 4. Is that okay? No, we've got a Superman situation, haven't we? The rays of light are coming out of the person's eyes and shining onto the duck. That is not a... No. Very well done if you spotted that. Excellent. Okay, let's think about images in mirrors. So I have a mirror here. I said to you, if you wanted to bring a mirror and a pen that stands up on its own and just put the pen in front of the mirror and have a think about, where is the image? Where is the image? Not a trick question. How am I going to hold this mirror and bring you down? Here, let's have a go. You've probably got mirrors in your house. I was hoping that you would, I just wanted to show off my cool new jumper. Hoping that you would bring a mirror. Here we go. Where's the, that's weird, isn't it? Where is the image? Do you know what I mean? Where does the image appear to be? Where does the image appear to be? Where does it appear that that image is? Okay, come here. This is getting uncomfortable. Quick nose blow. I was getting some really good answers to this on Facebook. One person said it's in front of the mirror. And I was like, yeah, it's not, is it? You don't sort of try and grab the image as it is here. So that's not right. People were saying inside the mirror, but then people were getting confused because obviously, like, you know that it's not. So is it on the surface of the mirror? Where does the image appear to be? How far away is the image? So let's go with the fact that the image is inside, or certainly appears to be inside the mirror. How far away is it inside? Oh, hello. How far away is it inside the mirror? Is it like just behind the mirror? Is it sort of 10 meters away? Where's it? This is brilliant. I should teach every lesson like this. I feel like I'm in a changing room. Where? how far? Right, shall I just give you the answer? So one of the things you need to know about the image in a mirror, which doesn't really make sense until we've looked at other images, is that it is something called virtual. A virtual image basically means it can't be projected onto a screen. So like, a cinema projector will project an image literally onto a screen so that people can watch it. You can't do that with an image in a mirror, can you? There's no way of projecting that image. It's a virtual image. It's sort of not really, it's like an illusion. But yeah, it can't be projected onto a screen. It's a virtual image. The other things about images in mirrors are they are the same size as the object, yeah? It's not like a magnifying glass, is it, where the image is bigger. It's the same size as the thing. If you're 5'5" in real life, you are 5'5" in a plain mirror. And the other thing is, you've probably said this, the image in the mirror is the same distance away as the object is from the mirror. Right? So if I'm like 20 centimetres away from this mirror, then the image appears to be 20 centimetres inside the mirror, okay? I have all the things that I've just said out loud, I've written on the screen because this is important for your IGCSE spec. Images formed by mirrors are virtual. More of this later when we talk about images that aren't virtual. The same size as the object and the same distance from the mirror as the object is. My goodness, so much coughing in my house. Right, I have to introduce you. If you've never met this guy, he just needs a quick introduction. This is Forkish. Forkish is, in fact, a Theatre of Science mascot. Quite a long time ago, I did a lesson about reduce, reuse, recycling, where I ranted quite hard about how people always use the word reuse wrong. And I had made this thing to demonstrate how we use the word reuse wrong. Like taking a glass to a weighing shop and refilling it with lentils, that is a good way of reusing something. This is not these workshop leaders who are like, oh, make a junk bottle. That's not good reusing. I've painted these forks, I said, in this lesson. So I can't reuse these forks, so I've made them harder to recycle. I've used loads of new sellotape and loads of new glitter, which is just more new, fresh plastic I've added to this thing. And in the end, it's not like a treasured toy, is it? It's going to last about 4 days, and then it's going to have to be ripped apart and put in the recycling, where I've created actually more plastic waste. Is what I said in the lesson. And everyone went, oh, he's so cute. Let's call him Forkish. So Forkish has taught, you guys have taught me to love. This is Forkish. He's been skulking behind us for ages because he won't fit on my little shelves. But anyway, Forkish wanted to be in this PowerPoint. So here we go. I'm really glad that you've all met Forkish now. Let's go into a bit more detail about how you draw a ray diagram. How do we see images in mirrors? Here we go. Right. Say you've got Forkish on the shelf above you. You've got superior shelves to me. Your brain knows that light travels in straight lines, okay? Your brain knows this. You have evolved, you have grown up on a planet where light travels in straight lines. So your eye sees light coming towards you from this direction. It sees the reflected ray travelling from the mirror, and it thinks, oh, okay, it must have come from over here. It extends the line for you. It assumes the light has travelled from sort of inside the mirror, if you like, and it creates an image of Forkish for you up here. It just seems incredible, doesn't it? But we've all seen images in mirrors, so that we know this is how it works. You end up, look, Forkish is the same size. He's the same distance away from the mirror as the real Forkish is from the mirror. And yeah, that's how it works. It's just your incredible brain creating an image for you, because obviously light carrying the information of Forkish, if you like, is coming at you in a straight line. So it just extends it over there. Isn't that brilliant? I have got some questions for you. At the risk of being a bit tedious, I am going to fix my mobile phone holder. I'm going to draw that on the board, because I think sometimes on the computer, like it's a bit too easy, isn't it, and clean. You need to watch a human struggling with this stuff to really work out how to do it. So let's say your question is, you've got a person, and let's give them a massive eye to make it easier. And they've got, what have they got? I don't know. They've got a cool new t-shirt with a lightning bolt on it. Ooh. And the question is, how does this person see the lightning bolt t-shirt in the mirror? Okay, so the first thing I would do is draw the image of the lightning bolt, because I know where that's going to be. It's going to be the same distance away from the mirror as the lightning bolt is, but on the other side. So I'm going to put it about there. People were getting all funny with me, including my son, about which way round the reflection was. I'm not going to worry about switching things over in the mirror. Doesn't come up at IGCSE. It's actually incredibly complicated how mirrors seem to switch things in the mirror. So, but anyway, that's my lightning bolt. So that's the image. So now I'm going to draw a straight line going from the eye to the lightning bolt, straight enough. But this ray of light, which is inside the mirror, which is not real, I'm going to do that a dashed line, okay? And the arrow is going into the eye. Whew. Okay, this is a good start. So I've got a ray of light shining into the eye. This one's real. And I've got the ray of light coming from the image, but that's a dashed line because it's your brain creating it. And then all I need to do is, I think I'll draw a normal in a different colour so that you can see it. So that's a dashed line at right angles to the mirror. And now, this was an IGCSE, I'd have to draw the ray of light which is shining from the lightning bolt to the mirror, and I'd have to carefully do it so that the angles of incidence and the angle of reflection were about the same. Yeah, I think that's all right. And I'll draw an arrow there to show light is going from the lightning bolt to the mirror, bouncing off the mirror and into the eye. I reckon these angles are about the same. That's the incident, isn't it? And that's reflection, and that's how the image is. Yeah, great. Okay, so that's what I want you to do twice in this question down here. I am going to stay as silent as I can because I think it's quite hard, this. Ideally what I want, really, if I was watching you, is I'd want to see you trying it loads of different times and getting it slightly wrong and crossing it out and trying again. A whole page full of sketches, I think, would be good for this, because once you've got it, but it can be a bit tricksy to get right. Right. Wormy has got a new shoe. If you printed out the printouts, you're going to have to draw Wormy her own new shoe, because I forgot to put the shoe on. Wormy has a new shoe. Draw a normal in the middle of the mirror, and then draw light rays to show how she can see her boss new footwear. You can start with the normal if you want. You don't have to. You can do it the way that I did it. Number 6, can you draw a diagram, please, to show how an ant sees their pants in the mirror? And can you label the incident ray, reflected ray, angle of incidence, and angle of reflection on your diagram? So remember, I would actually draw the image first. If you want to show how Wormy's drawing a shoe, I would draw the shoe first. And get that ray of light travelling from her eye to the shoe. I'll give you 10 seconds and I'll go through the first one. You can always be finishing off the second one if you like. Okay, let's have a look at Wormy then. So the first thing I would do, actually, I've draw the normal here. I would draw the shoe, I think. And then draw a line from the shoe going into her eye. But then I'd make sure that the line on the other side of the mirror that isn't really there is dashed, if you see what I mean. So the brain thinks that the light is coming from the shoe, but actually this ray of light isn't really there, okay, because this is inside the mirror. But this ray of light is real, so that's got an arrow. Well done if you did the arrow going into her eye. Then I put the normal on, then try to get it so that the ray of light actually shining off the shoe and bouncing off the mirror, the angles are the same on either side of the normal. Right, that's pretty good, actually. Right, let's have a look at this ant then. So again, I've drawn the pants on the opposite side of the mirror, same distance away. Straight line going all the way into the ant's eye, and then making sure that that's a dashed line on the other side of the mirror. And then draw the normal in, and then it's a bit fiddly, isn't it, this one? It's quite a small angle, shallow angle, but I reckon those angles are both the same, that's okay. So that works, right? We've got light shining from the pants, bouncing off the mirror into the eye, with the angle the same on both sides. But there is a straight line going from the pants to the eye, and that's how the ant is seeing their pants. Okay, and that's the incident ray, the one bouncing off. That's the reflected ray, the one bouncing into the eye. So the incident angle, it's a bit small, is the angle between the incident ray and the normal. Phew, there we go. Right, now if I'm not being patronising, this is definitely what I would do. If I was doing this in an exam, I would immediately be checking, are my arrows going in the right direction? Or have I accidentally done Superman? And are R and I the same? Oh, so sorry. You do get a little bit of leeway in an exam, you know, you don't have to measure it perfectly, but they should be able to eyeball it and at least see that that's what you were trying to do. Okay, that is the end of the lesson. I've got some GCSE questions for you. I'm just going to put you sort of one or two up at a time, give you 10 seconds to answer it, and then show the answer and then go on like that. If you haven't got the sheet, I suggest it's about a woman with a bow in her hair, because that's the only copyright-free image I could find. So if you haven't got the sheet, you might want to quickly sketch a woman with a bow in her hair. Obviously that's exactly what that is, and that's the mirror. It is quite useful, isn't it? They knew what they were doing when they did the diagram of the plane mirror, having little diagonal lines like that, because it shows obviously which is the shiny side of the mirror and which is the image inside the mirror. So yeah, make sure you do that as well. I've been a bit lazy with my lines. Okay, you ready? GCSE question number 1. A woman looks at her reflection. Draw a cross where the image of the bow on her head would be. 2 marks! 2 marks for that. Go on. This is a lot simpler than what you've just done. A woman looks at her reflection. Draw a cross where the image of the bow on her head would be. 10, 9, 8, 7. Aggressive. Counting. Learned it at teacher school. Can't unlearn it. 2, 1. There. You got it? So just on the other side of the mirror, on the inside of the mirror, but same distance away as the object is, as the bow is from the mirror, okay? So if you put the cross there, you get 1 mark if it's just on the other side of the mirror, like inside the mirror. And you get another mark if it's the same distance away. Well done. Again, it doesn't have to be perfect, you know, you could use your fingers, but you would expect the distance between the bow and the mirror and the distance between the image and the mirror to be roughly the same. Next question. Could you please draw a ray from the bow that reflects off the mirror and into the woman's eye? Draw arrows to show what direction the ray is travelling in, and then mark the angle of incidence with an I and the angle of reflection with an R. Off you trot. I will count to 20, but in my head, so to be slightly less aggressive and off-putting. Eight seconds. Okay, so you didn't have to draw the image, did you? It was just a ray from the bow that reflected off the mirror and into the woman's eye. So I did something like that. And I've drawn a normal as well, which I think you should always do in the exam so that you can show that you knew what you were talking about and that the angles are roughly the same. So if you've drawn the arrows going into her eye, give yourself 1 mark. And if the angle of incidence and the angle of reflection are more or less the same, give yourself a mark as well. And the angle of incidence is the one in between the normal and the incident ray, the light shining onto the mirror. And the angle of reflection is the angle between the normal and the one shining into the eye. Well done if you got that. So again, it seems probably quite straightforward now. In the exam, you'll be like, oh, which is the angle of reflection? Is it the one between the mirror and the ray? But no, the whole reason the normal is there is so we can work out these angles. Okay, last question. This one, a couple of people got it right in the last lesson on Facebook, but people were really struggling with this. So see how you get on with this. A mug is place 20 centimetres in front of a flat mirror. Is the image of the mug bigger and 20 centimetres away, bigger and 40 centimetres away, the same size and 20 centimetres away from the mug, I should be saying, or the same size and 40 centimetres away from the mug? You put a mug 20 centimetres in front of a mirror. Is the image bigger and 20 centimetres from the mug, bigger and 40 centimetres from the mug, the same size and 20 centimetres from the mug, or the same size and 40 centimetres from the mug? People were really struggling with this on Facebook, which kind of pleased me. I was like, well, it's good that I'm testing you on this now. Have you got it? The answer, of course, is the same size and 40 centimetres from the mug. Did you get that? The same size and 40 centimetres. Yeah? You're all right with that, aren't you? Here we go. So you've got a mug, you put it 20 centimetres away from a mirror. The image is also 20 centimetres away from the mirror, isn't it? So altogether, the image of the mug is 40 centimetres away from the mug. I suspect most people who got that wrong, it wasn't that they didn't understand it, it was because they hadn't read the question properly. Isn't that a fabulous lesson for everyone doing IGCSE? Okay, you lot. That was good, wasn't it? Okay, that is the end of this lesson. Thank you so much for going. If you want to pay me, that is really helpful. So a lot of people who come to these lessons are supporting me and glancing around for the nice things I send you if you support me. With £5 a month. So I do an all ages lesson, which you can come to this week. IGCSE and all ages lesson are two separate lessons. We're both doing waves this term, but I've made it that if you're doing IGCSE, you can come to the all ages lesson, which is on this week, because it's on colour. So it's very relevant to what we're doing now. But it doesn't so much crop up in your syllabus. So yeah, the all ages science lesson is free. The IGCSE physics lesson that you are at is free. The Lego Storytime show, which I do on Thursdays, is free. And if you want to, you can go to my About section and follow this link to this website called Coffee and support me with £5 a month. Or you can just like search on the internet, Coffee Theatre of Science. And it takes you to this website where sign up with £5 a month. I will send you nice things. I will send you rainbow glasses, how very appropriate, which make you see rainbows, to say thank you so much for contributing towards my wages. It is massively appreciated. I mean, this is clearly the best job ever. You know that pile of papers that I was telling you to go away at the start of the lesson? Oh, here we go. I send you Theatre of Science magazine as well. I write a magazine every so often. So if you sign up now, I will send you this issue on mould. It has a junior and adventure and a little comic strip about the real discovery of penicillin and how there were a lot more people involved than we think. One of them was a disabled woman. I know, right? You'll have to subscribe to the magazine to find out more about her. Okay, just going to go over to my Facebook post and see if anyone has said hello. And after that, I'm going to go because I have got my all ages science lesson on colour to teach on Facebook in 20 minutes. If you're watching live. If you're not watching live, then don't worry about it. It's already on YouTube saved for you, I'm sure. Okay, I'm just going over to my Facebook page because every time I'm live on YouTube, I put up a post saying, you can always comment or ask a question here if you're watching live, because there's no comments on YouTube, as you'll have noticed. Still waiting for it to load up. Still waiting. There must just be so many comments. Oh, hello, Tiger and Bird. Oh, big question. Hello, Sky and Evie. Sky and Evie, I'm going to say hi to you before I target this question. Sky and Evie, hello. Thank you so much for coming. Tiger and Bird, please could you explain how if a black hole doesn't emit any light, how scattered and reflected X-rays of a torus can be seen? Yeah, it kind of can, like really quickly. A black hole does not emit any light, no. All the waves that get too close to a black hole obviously get sucked in. But black holes have got enormous amount of gravity, right? You know how, like, maybe this is not what you meant. Like, sorry if this is patronising and you know this already. But you know how, like, the moon is attracted to Earth because of Earth's gravity, okay? Moon is going around the Earth because of gravity. It's kind of attracted to Earth, it's constantly falling towards the Earth, but it keeps missing, is probably the best way to describe it. So obviously there is a whole ring of stuff around a black hole, which is being attracted to it because of gravity, but is kind of spiraling, and all that stuff is the stuff that is giving off X-rays, as far as I know. In this job, I constantly have to look up how black holes work and what they are, and then I just keep forgetting. So I'm very sorry if that is not quite correct, but the X-rays are definitely given off by like the very edges of a black hole. I just can't remember the precise mechanism. Now, anyway, I've got to go. Time to go to bed. Isn't that convenient? Thank you so much for coming. Have fun looking at black holes today. And I might see some of you for my all ages lesson. If you like to watch on YouTube, it's on YouTube tomorrow, Thursday at 12 o'clock. So I might see you then. Bye.